Assalamualaikum warahmatullahi taala wabarakatuh, and very good morning to everyone who joined this session this morning. Okay, I hope everyone is okay, fine, happy, and ready to continue with our lesson today. Okay, Waalaikumsalam Muhammad Firdaus. Good morning, Cik Long Sun. Okay, let's start with record this session first. Okay, so let's recap with what we have discussed yesterday. Okay, yesterday we start chapter 3, which is time response analysis. So we have discussed on what is a time response. I have explained to you the function of time response. What is time response? Okay, and then we go through the step in order to get the time response equation. Okay, so we have covered step number 1, producing ODE. Okay, basically it based on the second chapter. Okay, but we just need to separate the output and input into separate part. Okay, and then yesterday we also discussed on Laplace transform. Okay, I explained to you on how to use the table. The important part is how to convert from second differentiation and first differentiation into Laplace form. Okay, because that is the important part in the ODE equation, differentiation part. Alright. Okay, we do step number 3, apply initial condition. Okay, step number 4, apply input signal. Okay, it's depend on type of input. Okay, if your input is RAM input, then you're going to apply 1 over S square into the Laplace equation. Alright, so after we apply the input, okay, basically we're going to after we apply the input, we're going to do the partial fraction decomposition. Okay, I have shared the table for partial fraction table where you can convert from a function into partial fraction. Okay, and then right, so after you convert into partial fraction, then we need to solve for the parameters. So there will be A, B, C, and D. Okay, or E, depend on the function. How many parameters will be in your partial fraction equation, right? So we're going to use reminder theorem, okay, which we haven't discussed yesterday, right? But today we're going to discuss on that reminder theorem. Okay, after we get the parameters value, A, B, C, D, or F, okay, then we do the Laplace inverse. Okay, so in order to inverse the Laplace form, again we're going to compare with the Laplace table in order to get standard form, so that we will get a common function in the table. Alright. So yesterday we stopped until this example. Okay. So step number 1, ODE. Okay, based on the analysis of free body diagram, we get the equation. Then we put all the equation into the initial equation. Then we separate the input and output. All right. So after that, we apply the initial condition. Okay, the initial condition is given there. Okay, x not 0 is 0 and x dot not 0 equal to 0. Okay. After that, we apply the input. But before we apply the input, we need to write the equation in form of output equal to transfer function multiplied with the input. Okay. So yesterday we stopped up until partial fraction decomposition. Okay. So what we get here is partial fraction decomposition. Okay, we get A over S plus B over S plus 1 plus C over S plus 2. Okay. So for today, we're going to discuss on how to use a remainder theorem in order to determine the value for A, B, and C. Okay. So this is the remainder theorem. Okay. So the remainder theorem said that a function is normally in form of numerator over a denominator. Okay, so here n is represent the numerator and d is denominator. Okay, S here meaning it is in Laplace form. If the function is in the function of S, so meaning the equation is in Laplace form. Okay. So the transfer function, bukan transfer function ni. Basically the transfer function pun boleh lah. The function can actually be converted into the partial fraction where it contain the summation of AI over S minus Si. Okay. So this is similar to the one that we have just now. Okay. 3S plus 2. Okay, so we have 3S plus 2 is the numerator. Then the denominator is S plus 1, S plus 2 kan? S plus 2. Okay. Okay, S plus 2. Okay, where we convert that into a partial fraction, we have A over S plus B over S plus 1 plus C over S plus 2. Okay. So this part here is actually represent the numerator over denominator, and this part here is represent for this part here. Okay, summation of AI over S minus Si. Okay. Alright, so in order to determine AI, okay, so you can see that numerator over denominator, okay, numerator over denominator, it will multiply with the denominator of AI, okay. So you can see here denominator of AI, S minus Si. And then we're going to consider S equal to Si. Okay, we're going to consider S equal to Si, where it comes from the denominator here. We consider S minus Si equal to 0. Therefore, S equal to Si. Okay. All right. let's use the reminder theorem in order to determine for A, B, and C. Okay, so we will follow the this step here. So the first one is A will equal to, so S here is the denominator for the A. It will multiply to the numerator over denominator. Okay, so we have numerator over denominator is 3s plus 2 over s plus 1, s plus 2 multiply with s, where we consider s equal to 0. Okay, because it's based on here, s equal to 0. Okay, so we consider s equal to 0. All right. So now we can cancel this part to this part. Okay, then cancel s. And then we're going to replace all the s term will become 0. Okay, so this one will become 0. This one will become 0. This one will become 0. Okay, so it will left us with 3 multiplied with 0 is 0 plus 2, 2 over, right? And then 0 plus 1 is 1. And then 0 plus 2 is 2. Okay, so therefore 2 divided by 2 is 1. Okay, so A is equal to 1. Okay, I hope you can follow. Alright, so let's do for B. Okay, similarly, B is equal to, the denominator of B will multiply to the numerator here. Okay, so therefore we're going to have 3s plus 2 divided by s plus 1, s plus 2 multiply with s plus 1. Okay, because s plus 1 is the denominator for B. And then we're going to consider s equal to minus 1. Okay, because based on the denominator of B, we said that s plus 1 equal to 0. Therefore, s equal to minus 1. Okay, so similar step, we're going to cancel. Okay, this part will be cancelled with s plus 1. And then we're going to replace this to be minus 1. This one will become minus 1. This one will become minus 1. Okay, so we have 3 multiplied with minus 1, minus 3 plus 2, which is minus 1, over minus 1 multiply with minus 1 plus 2, it is positive 1. So therefore, it is 1. Okay, minus divided by minus, so it positive 1. So B is 1. Okay. All right, then we solve for C. Okay. C is equal to numerator over denominator, which is 3s plus 2 divided by s plus 1, s plus 2 multiply with s plus 2. Okay, because the denominator of C is s plus 2, where we're going to consider s equal to minus 2. Okay, again, based on the denominator of C, so s plus 2 equal to 0. So s equal to minus 2. Okay, similar step. Okay, we're going to cancel s plus 2, s plus 2. And then we're going to replace minus 2 into the s term. Okay, so this one will become minus 2. This one become minus 2. This one will become minus 2. Okay, so we have 3 multiplied with minus 2 is minus 6 plus 2 is minus 4. Okay, divide by, okay, minus 2 multiplied with minus 1. So 2, positive. Okay, minus multiplied with minus, positive. Okay, positive 2, so we get minus 2 for C. Okay. All right. So therefore, I'm going to continue here. Therefore, our x naught s, the output in Laplace is equal to 1 over s plus 1 over s plus 1 minus 2 over s plus 2. Okay. So we're going to inverse going to do the inverse Laplace 2 over s plus 2, right? So s naught s inverse, it become s naught t will equal to 1 over s is if you refer to the table is step input, so it become 1. Okay, and then 1 over s plus 1. Okay, let's refer to the table. Okay. Oh. Okay. Okay. All right. So referring to the table, s plus 1 is in this form. Okay. 1 over s plus 1. So if we compare to our term, which is 1 over s plus 1, so we can say that okay, alpha is equal to 1. Okay, so therefore we inverse here to the time function. So it is exponent negative alpha t. So alpha is 1, therefore we get exponent negative t. Okay, so the other one is 2 over s plus 2. Okay, so we're going to separate 2 multiply with 1 over s plus 2. Okay, similarly alpha is 2. So we get 2 exponent negative 2t. Okay. So that will be the solution. Okay. 1 ini minus kan? Minus. 1 plus exponent negative t minus 2 exponent negative 2t. Okay, so that is the time response equation for a mass spring system, a mass spring damper system. Okay, so basically again, if you want to know the behavior, we're going to plot the equation for x naught, okay, by replacing t, and this is x naught. Okay, so you can 0, 0.5, 1, 3, 5, 10, 100, infinity. Okay, I just put any values there. Okay, so basically we will be able to plot. Okay, so maybe you have something like this. Okay, if you want to know the behavior, so plot the graph there, right? Okay, so basically we cover all the steps in time response derivation. Okay, any questions so far? Do we need to use graph? Do we need to, normally it won't ask you to plot the graph actually, but here I just want to show you the application of the time response equation that you have derived. Okay, so you know the function of this time response equation. Okay, so it is actually to know the behavior of the system. Okay, but normally they won't ask you to plot the graph for the time response equation. But later for first order, second order, yes, you need to plot some of the graph. Okay. Any more question? Ada lagi soalan tak? Okay, so far so okay. All right. Okay, let's do the next example. I'm going to do it here. Okay, so example 2 is okay, d square y over dt square plus 5 dy over dt plus 6y equal to 12 exponent t. Okay, with y0 is equal to 2 and y dot 0 is equal to 1. Okay, so in this example, you can see that the initial condition is not 0. Okay, so it's given that y0 is equal to 2, meaning the output is not starting from 0. The output is start with 2. Okay, and then y prime, y dot 0 is the gradient at t equal to 0 is equal to 1. Okay, for the output graph. Okay, so we need to replace the value instead of having 0 initial condition. So you can expect the equation we have some value here. Okay. All right. So what will be the Laplace transform for this is step number 2, because step number 1 is the ODE is already given. So step number 2 is Laplace transform. Okay, can you tell me the Laplace form for the second differentiation? Anyone? Anyone? S square? SYF?
S square
Minus?
plus
Minus, correct.
x minus
Minus S? Y0?
s y0 plus
Minus?
y minus y prime
Y prime?
0.
0.
0.
Right, thank you. Muhammad apa tadi? Okay, Muhammad Imran. Alright, that is the first difference, second differentiation. Alright, and then for the second part is the first differentiation. So 5 multiply with S ys minus y0. Okay, you should remember this. Okay, you should remember form for second differentiation, the form for first differentiation. Alright, then we have plus 6ys will equal to 12 exponent t. Okay. Alright, so we're going to apply initial condition. Right, so we're going to apply the initial condition. Okay, it said that x not 0 is 2. So this one is 2. This one is 1. This one is 2. Okay, so therefore our equation will become s square ys minus 2s minus 1 plus 5sys minus 10. Okay, remember 5 multiplied with 2. So minus 10 plus 6ys, okay, will equal to 12 exponent t. Okay, let's rewrite the equation. So we put all the s term to the same place, s square ys, 6ys plus 5s ys plus 6ys minus 2s minus 1 equal to 12 exponent t. Okay. Let's do step number 4. Okay. Apply input signal.
Doktor, minus 10, doktor.
Oh, minus 10, minus 10 lah. Okay. Minus 10, minus 10, minus 11 lah. Tinggal pula. Minus 11. Okay. Okay, minus 1, minus 10, minus 11. Yes, alright. So we apply the input signal. In this case, we consider the input signal is UI is equal to ET. Okay. This function here. Right. So meaning we're going to transform ET into the Laplace. Okay. So let's refer to the table. Okay, let's refer to the table. Okay. So here we have our function is exponent t. Okay. So therefore we consider alpha is equal to minus 1. Okay, because if you replace exponent negative 1t, so you get exponent t. Alright. So therefore in the Laplace it will become 1 over s minus 1. Okay. So we put that into the equation. Okay. So we're going to factorize ys. So ys here is equal to multiply with s square plus 5s plus 6 will equal to 12 over s minus 1 multiply with 1 over s1 and then plus 2s plus 11. Okay. So therefore ys is equal to 12. Ini kita akan darab ke atas lah. Okay, so supaya pembawah dia sama. So we have 12. Tolong check 2s square plus 11s minus 2s minus 11 divide by s minus 1 and then the part s square plus 5s plus 6 can be factorized. So it become s plus 2s plus 3. Okay. So s plus 2, s plus 3, if you multiply, it will become s square plus 5s plus 6. Okay, so if we can factorize the function, the polynomial function, then we should factorize it. Okay, so therefore our equation will become 2s square plus s minus 2. 11 minus 2 is plus 9s. Okay, and then 12 minus 11 is plus 1. Okay, divide by S minus 1, S minus 2, S plus 3. Okay. Please check kalau saya ada, kadang-kadang saya jelah tukar plus minus semua tu. Saya confuse. Alright. Kalau you dapat detect, you bagi tahu eh. Right, so step number 5 is partial fraction decomposition. Right, so we're going to rewrite the function here, 2s squared plus 9s plus 1 divided by s minus 1, s plus 2, s plus 3 will equal to, alright, so we do the partial fraction decomposition. Again, we're going to refer to the table, okay, table that I've shared in the WhatsApp, okay. Open the table. Okay, there is 5 function there. So which one is similar to our function here? Number 1, number 2, number 3, number 4, number 5.
Number 3.
Number 2.
Okay.
Number 3.
Okay, the answer is number 3, okay? The answer is number 3. Okay. If you see the function, the numerator function is square, meaning s square plus s plus constant. Okay. Alright, so that is similar, and then the denominator part it is in factorial, x minus a, x minus b, x minus c. So this is similar for to us. S minus 1, S plus 2, S plus 3, right? So therefore, it will become A over S minus 1 plus B over S plus 2 plus C over S plus 3. Okay? So, since the partial fraction is in terms of summation of AI over S minus SI, which is, if you refer to the partial reminder theorem, okay, so it is the same as the reminder theorem theory. So we can use reminder theorem. Okay, there is also a function that we cannot use the reminder theorem. Okay, so for this example, we can use a reminder theorem, right? So therefore, we have. Okay, let's write. Okay, reminder theorem. Reminder. Okay, reminder theorem. So we have A is equal to 2s squared, the numerator, plus 9s plus 2 over denominator, which is s minus 1, s plus 2, s plus 3, multiply with the denominator of A, which is s minus 1, and then we're going to consider s equal to 1. Okay, from here, s minus 1 equal to 0, s equal to 1. Right? So please calculate for A. Right, so you can cancel this to this. And then you're going to replace this to be 1. Right. So we're going to write the same for B and C. By now you should be able to write all this. B equal to 2s squared plus 9s plus 1 divided by s minus 1, s plus 2, s plus 3 multiply with s plus 2, where we consider s equal to minus 2. Okay, so you get B. Then for C, 2s squared plus 9s plus 1 divided by s minus 1, s plus 2, s plus 3. Multiply with the denominator of c, which is s plus 3. Then we consider s equal to minus 3. Okay, so this one cancel with this one cancel with this one, and here it is minus 2. This one only minus 2. Okay, minus 2, minus 2, minus 2, minus 3, okay. So what will be the value for A?
One.
Okay,
1.
1, right. B,
3.
3. C, minus 2. Anyone else? C equal to minus 2. Okay, everyone get minus 2, okay? Alright, so therefore, our output in Laplace form is equal to 1 over s minus 1 plus 3 over s plus 2 minus 2 over s plus 3. Correct, eh? Check balik. S minus 1, s plus 2. Okay. Alright. Okay, so step number 6 is Laplace inverse. Okay, so we're going to inverse x naught s Okay, so basically it will be in terms of exponential. So 1 over s minus 1 is exponent t. Okay, plus 3 exponent negative 2t minus 2 exponent negative 3t. Okay, so that will be the time response equation. Right? Okay. All right. I think it's straightforward. Okay. As for example 3, this is just for partial fraction. Okay. So let's convert this into partial fraction. Okay, so we're just going to refer to the denominator of the function. Okay, we're going to refer to the denominator of the function. Okay, if the denominator of the function can be factorial like this, so just going to be a over s plus b over s plus 1 plus c over s plus 2. Okay. So basically this 3s plus 2 is similar to this example, this one here. Okay. System here. Right. So we're not going to do this. Right. But sometimes, okay, if we refer to example 4 here, okay, the term s square plus 2s plus 5 cannot be factorized. We cannot factor this function, this polynomial. Okay, we cannot factor this. Right? So if we cannot factor this, so let's check with the table. Okay, the partial fraction table. So which function it will be? 1, 2, 3, 4, 5. Okay? Right.
Right.
Vina. The answer is 5. Okay? Because if you refer to the table, okay, function number 5 is, we look at the denominator. Okay? We not really, bukan not really care, ada lah effect for the numerator there. Okay? But basically the most important part to look at is at the denominator. Okay, so if the denominator cannot be factorized, like in function number 5, okay, so because in function number 5 there is x squared plus bx plus c. Okay, so we cannot factorize that. So you can see that the partial fraction here it become bx plus c for the x squared plus bx plus c. Okay, so therefore in our case here, the partial fraction will become a over s plus bs plus c over s squared plus 2s plus 5. Okay. Alright, so since this is not the same form as the remainder theorem, okay, the remainder theorem need to have s plus, s minus or plus something at the denominator. But now we have s square plus 2s plus s, okay. So we cannot use remainder theorem in order to solve for a, b and c. Okay, if you use remainder theorem, you only left with 2 equations but 3 unknowns. Okay, so here we're going to use I'm not sure what is the method, the name of the method, but it's actually by comparing the left side to the right side. Okay, so first let's make the denominator of the right side similar to the denominator at the left side. Okay, so it is similar to, okay, 5. Okay, the denominator is s square plus 2s plus 5. Okay, so it's actually similar to by multiplying this. Okay, so you will have the denominator will become the same as s square plus 2s plus 5. Okay, and the numerator will become as square plus 2as plus as plus bs square plus cs. Okay, so we need to compare left side to the right side. Okay, so since denominator is already the same, right, so we're just going to consider for the numerator. So we're just going to write 5 equal to, okay, if you, okay, s square, so we have a plus b s square, and then we have plus, ini as, ini bukan as kan, ini 5a. ES, ini adalah 5a. 5a. Right, this is 5. Okay. So we have 2s, cs. Say 2a plus c s plus 5a. Okay. So if going to compare left side to the right side, okay, so for the left side, this is actually 0s square plus 0s plus 5. Okay, so now you can consider AB to 0, 2AC to 0, and 5A to 5. Okay, so from there, let's write 5A equal to 5, therefore A is equal to 1, right? And then we have A plus B equal to 0, okay, for this part here. Okay, A plus B equal to 0, since A is already known, so therefore we get B equal to minus 1. Okay, and the last one is 2A plus C equal to 0. Okay, A is already known, 1. So C is minus 2. Okay. So we're going to replace into the equation. So our x naught s is equal to 1 over s. B is minus 1. So plus minus 2 apa? Minus 2s minus s minus 2. B is 1, right? So minus s minus 2 over s square plus 2s plus 5. Okay, so we can rewrite this to become 1 over s minus s plus 2 divided by s square plus 2s plus 5. Okay. So now we need to do the Laplace inverse. Okay. So in order to do Laplace inverse, let's refer to the table. The table, okay, this table. Okay, so which function is similar to our function, which is s plus 2 over s square something lah, saya tak ingat apa s square apa. S square apa nama dia? Okay, which one? Is it this one? Is it exponent 1 over s plus alpha? No, we don't have that. Is it our function is similar to this one? Okay. Is it to this one? This one? This one? Okay. So our function apa? Our function cuba sebut our function. S plus 2
S plus 2
over
divide S
square
square plus 2S plus 5.
plus 5.
Yes.
Right.
Yes,
Okay.
yes.
All right. So so we only have this 1, 2, 3, 4, 5 function, but none of our function is similar to that. Okay. So basically, we need to manipulate a little bit such that it will be similar to the standard function here. Right. So okay, we can see the numerator we have s plus 2. Okay, so it is similar to this one here, s plus 2. Okay, so let's try with this function here. All right. Okay, so the denominator function is s plus alpha square plus beta square. Okay, so try to think what is the value for alpha and beta such that if you expand the function, it will become s square plus 2s plus 5. Okay, let's try. Since the upper one is s plus 2, let's try s plus 2. Okay, s plus 2 square plus kalau S plus 2 is S square plus 4S plus 4. Okay, tapi this is 4, this is 2. Okay, so S plus 2, we cannot use S plus 2. Okay, so anyone? Let's try S plus 1.
S plus 1.
Okay, let's try S plus 1. S plus 1 square is S square plus 2S plus 1. So for beta 1, 1 campur 4, 5. So plus 2 square. Okay. So therefore, right? So S plus 1 is correct. Right, S plus 1. Okay, let's go back to here. Tak ada, di sini lah. Tak ada space. Okay. Alright, so let's write the equation. Okay, so we get the denominator. Right, so the denominator is right, so we have S plus 1 square plus 2 square kan? 2 square. Okay, so therefore alpha is 1. Inilah alpha is 1, beta is 2. Okay, so here is S plus alpha. So we write the equation. So S plus 1 over, tapi here we have S plus 2. So we need to have another 1. S plus 1 over S plus 1 square plus 2 square. Okay. Okay, so basically that one, okay, this is similar to 1 over S minus S plus 1 over S plus 1 square plus 2 square minus 1 over S plus 1 square plus 2 square. Okay. Nanti because the denominator is the same, so it also become S plus 2 if you multiply that together. Right, so let's do the inverse Laplace. Okay, I'm just going to write here x naught t equal to 1 over S is 1. Okay, and then we have S plus 1 over S plus 1. That one is similar to the table that we refer just now. It is exponent negative t cos 2t. Exponent negative t cos 2t. Okay, it is minus exponent negative 2t cos exponent t kan, exponent t bukan 2t, exponent t cos 2t because beta is 2. Right, and the last term 1 over S square plus S square, if we refer to the table, okay, this is the value. Okay, 1 over salah. This is the value, salah. This one. 1 over S plus alpha square plus beta square, 2 square. Okay, so we can separate it because it is 1. Our function is 1 over S plus 1 square plus beta is 2 square. So that is similar to beta over S plus alpha square plus beta square. Okay, so at the denominator, beta is equal to 2. Okay, so apa kali dengan 2/1. Right, so x multiplied with 2 is, so x is 1/2. Okay, so therefore we can rewrite the function. It is similar to 1/2 multiply with 2 divide by s plus 1 square plus 2 square. Okay, because the beta should be similar to the upper part. Okay, so therefore we have a gain of half, 1/2. Okay, so therefore our function in t is exponent negative t, because alpha is 1. Okay, alpha is 1 and beta is 2, so it is sine 2t, but it is 1/2. Okay. Okay, so the final one will be, okay, so final one will be 1 minus exponent negative t cos 2t minus 0.5, 1/2 saya tulis 0.5 lah, 0.5 exponent negative t sin 2t. Okay, that will be the answer, the Laplace inverse for the equation. Okay, let's write here. Let me write here. So x naught t is equal to 1 minus exponent negative t cos 2t minus 0.5 exponent negative t sin 2t. Okay, so that is meaning this example show you in order to inverse the Laplace, we need to manipulate a little bit of our function so that it will be similar to the standard form that we're going to use. Okay, any question? Yes. Tak sempat baca nama. Siapa yang raise hand tadi?
Saya doktor.
Yes. Muhammad Firdaus.
Nak tanya, kalau macam untuk case example 4 ni, kan
Yes.
kita tak boleh remainder theorem kan?
We don't use remainder theorem because we cannot factorize s square plus 2s plus 5. And also it is not similar to the remainder theorem. The denominator part should be in s minus something. But if you have s square plus 2s plus something, so we cannot factorize that, so we cannot use the remainder theorem.
So kalau macam kita apply method yang tak apply remainder theorem ni dekat soalan yang boleh pakai remainder theorem,
Boleh? Oh, boleh juga.
dia sama juga?
Benda yang sama juga. Yes.
Okay. Thank you, doktor.
You can also use a comparison method here, even if the denominator can be factorized, meaning you can use a remainder theorem. You can also use this method. Okay, you can use any method that you familiar with. Okay, because I believe when you learn about partial fraction before, you use this kind of method, right? Comparing the left side to the right side. Okay. All right. So basically, we have cover for the time response, derivation of time response equation. Okay. So all the example here is showing you the tricks that maybe occur in it's not actually a trick. It's a common thing that will occur when you need to do time response analysis. Okay. So if your system is complex, so you expect a more complex function. Okay. If the system is simple, okay, the function will also be simple. Okay. All right. Okay. Okay. Once we get the time response, okay, let's break for 5 minutes before we start with the other part of chapter 3. Okay. So I will let you rest for 5 minutes to digest all the information that you have received just now. So let your brain rest a little bit. Okay, after 5 minutes, we're going to start with classification.
Betul.
Assalamualaikum Doktor.
Yeah.
Can Doktor repeat again how to inverse the lab list? I don't get
How to inverse?
the lab list, the previous question.
Is it for example number 4 just now?
Yes.
For the inverse part only, right?
Yes.
Okay, for the inverse part only. Okay. So let's tell me the function. X naught S is equal to 1 over S minus
S plus 1
S plus S plus 1 over S plus 1 square plus 2 square minus 1 over S plus 1 square plus 2 square. Right. Okay, so which part you don't understand?
The 1 over S plus 1 square plus 2 square.
Okay, let's just focus on that. Okay, so I'm going to write that 1 over S plus 1 square plus 2 square. Okay, so now we're going to refer to the table. Okay, so from the table you can see it is similar to beta over S plus alpha square plus beta square. Correct. Okay, so we can see that at the denominator part, it is similar, right? So we can see, okay, alpha, we can say, okay, alpha is 1 and then beta is 2. Okay, but if we consider beta is 2, then your equation will become 2 over S plus alpha square plus 2 square. Correct?
Correct.
Okay, but now our term here is 1. It is not 2. Okay, so what we're going to do is we're going to multiply with 0.5 multiply with 2, okay, over S plus alpha square plus 2 square, which also similar to 1 over S plus 1 square plus 2 square. Setuju tak?
Yes.
Alright. So that's why if you refer to this one here, okay, so it is similar to 0.5, we separate, multiply with 2 over S plus 1 square plus 2 square. Okay. So if you going to inverse the Laplace for 2 over s plus 1 square plus 2 square, that one we similar to apa tadi? Exponent negative t, because alpha is 1, so exponent negative t. Okay. Can you read the function from the table? Exponent negative alpha t sine beta t, right? Do you know how to refer that, Abu Khairi?
Yes.
Okay, it is from the table. Okay, so from the function here, from this function here, okay, we said, okay, this is beta equal to 2, okay, beta, and this is alpha. Okay, so therefore the function will become exponent negative t sine, because alpha is 1, okay, sine 2t. Okay, but then we need to multiply here 0.5. Okay,
Right.
so that's why when you inverse x naught t will equal to 1 over s is 1, and then the second part is minus exponent negative t cos 2t, alright, and then minus to the third part is minus 0.5 exponent negative t sine 2t. Okay. Okay. Khairi? Okay tak Khairi? Okay. Alright, let's start with classification of control system. Right. Alright, so we do a classification on the any control system, because by knowing the class, the group, the type of the control system, we will be able to predict the behavior of the system. Okay. Okay, so that's why we do a classification. We class the system. Okay, so first, in order to do the classification of a control system, we're going to consider the open loop transfer function. Right, so this is the first time you hear the open loop transfer function. Okay, open loop transfer function. Right, open loop transfer function. Or sometimes I just use OLTF. Okay, the other one is closed loop transfer function. Closed loop transfer function, CLTF. Okay. So sometimes in order to analyze a control system, sometimes we use closed loop transfer function. Okay. For example, in time response analysis, we consider the closed loop transfer function. Okay. We need to simplify all that until we get one transfer function. That one is called as a closed loop transfer function. Okay. And then we derive the time response based on the closed loop transfer function. Okay. The other one is open loop transfer function. Okay. Example of analysis that use open loop transfer function is stability analysis, boat diagram, Nike's, root locus, and all that is based on the open loop transfer function. Okay. So you will need to know how to get a closed loop transfer function of a system, and also open loop transfer function for a system. Okay. So let's consider this block diagram here. Okay. Anyone can tell me the equation for the closed loop transfer function? Do you know the closed loop transfer function?
You work kat you Unity Y.
Firdaus? Okay, no. Okay, you already used that during block diagram manipulation.
Unity
Okay.
Y.
So if you have this block diagram, the closed loop transfer function will become
U negative Y.
closed loop transfer function will equal to kg over 1 plus kgh. Okay, let's consider this is h here. Okay, so kg over 1 plus kgh is the closed loop transfer function. Okay, for the open loop transfer function, okay, you're just going to multiply the feed forward transfer function with the feedback transfer function. Okay, or feed forward gain with the feedback gain. So it become kgh. Okay, that's how we determine the open loop transfer function. Sometimes we can also use the closed loop transfer function in order to determine the open loop transfer function, where we consider this part to be the open loop transfer function. Okay, so closed loop transfer function is actually equal to feed forward gain divide by 1 plus open loop transfer function. Okay, so for closed loop it is feed forward gain. Any gain at the feed forward path, okay, you're going to multiply that and then divide by 1 plus open loop transfer function, where open loop transfer function is feed forward gain multiplied with the feedback gain. Okay, so that's how we determine open loop transfer function and closed loop transfer function. Okay, so just remember, closed loop transfer function is kg over 1 plus kgh or minus kgh, right? And for the open loop transfer function, it is kgh. Okay, so we're just going to refer any gain at the feed forward multiply with any gain at the feedback. Okay, feedback. All right. So that's how we determine open loop and closed loop transfer function. Okay, so classification will be based on the open loop transfer function. Okay, so any transfer function or either it is open loop or closed loop, you can find the transfer function is in form of, okay, let's say this one here, you maybe have something like s plus 1, s plus 3 over s cube s s square plus 3s plus 5. Okay, so you may be found this kind of transfer function, or you also find the transfer function is in a polynomial form. Okay, meaning we're going to expand that. Okay, so we maybe have s square plus 4s plus 3 divide by plus 3s cube plus 5s square. Okay, you may either find the transfer function in this form, which is the general form is this one here, or in this form. Okay, S meaning it is in Laplace form. Okay. Okay, so by knowing the open loop transfer function, we can do the classification. Okay, there are 3 types of classification. Okay, there are 3 types of classification. Okay, the first one is based on order. Okay, based on order, where here we can say that order is the highest order of S at the denominator. Okay, meaning we're going to look at the denominator and then we're going to determine what is the highest order there. Okay, so for example here, right, so for this transfer function, okay, we look at the denominator. Okay, what is the highest order there?
Four.
That's 4.
4, Doctor.
Right, so the highest order is this one here at the first term. Okay, so we look at the first term there. So the order is 4. Okay. All right, the second one is based on rank. Sometimes we classify a system based on rank. Right, so based on rank, it is n minus m. Okay, what is m? What is n? Okay, n here is this one here. Okay, n is actually highest order of S at the, okay, bukan numerator, denominator. Denominator. Okay, which is the order just now lah. N is actually order. So highest order of S at the denominator. Okay, while M is the same, highest order of S at the numerator. Okay, M is for the numerator part. Okay, for the upper part. Okay, so again, if you refer to this example here, okay, so we can say N is 4, M is 2. Okay, M is 2 because highest order at the numerator. So at the numerator, the highest order is S square. So M is 2. Therefore, rank is N minus M. So 4 minus 2 will give you 2. Okay, so if the system is having open loop transfer function, the order is 4 and the numerator, the M is 2, then the rank is 2. All right. Last one is based on class. Okay, based on class. Okay, so this is wrong. The definition here is wrong. Okay, so for the class L, class or type, this is actually the definition is the highest factorial of S at the denominator. Okay, the rank class or type, or we call it L. Okay, the definition is the highest factorial of S at the denominator. Okay, meaning we're going to look at the denominator. Okay, if you're going to factorize the denominator, okay, you're going to factor the S there, what will be the highest order? Okay, simply we just look at the last term. Okay, so the last term is S square. Okay, so therefore the class is equal to 2 for this example. Okay, but if you're going to factorize, you will get S square plus S2 plus 3S plus 5. Okay, so the highest factorial of S is 2. Factor the S, the highest order is 2 for the denominator part. Okay, so that is the class. Okay, so 3 type of classification: order, highest order of S at the denominator; rank, the difference of order of denominator minus order of numerator, and then class, okay, or type is the highest factorial of S at the denominator. Okay. All right. So I hope you get that. Okay. Let's try the example. Let's try the example here. Okay. Let's determine the order, rank, and class. Alright, for A, what is the order?
4.
Okay, 4, we look at the first term. At the first term, it is 4. Alright, rank. 4
Three.
minus 1.
1.
Okay, S to the power of 1, so it is 3. Class, look at the last term, so 1. Okay. Okay, B, 5. Okay, you're going to expand that. Okay, rank 5 minus 0, 5. Okay, because this is S0. And then class is 3. Okay, you already factorized that, so we look at the factorial order there. All right, last one is order
3.
3, right?
3.
3. Rank 3
One.
minus 2, 1. Rank you're going to class I think is 0. Okay, because you're going to get S cube plus 3S square
Order.
plus ini 1 S square dah plus 8 plus 16 kan. S. Okay, so at the last term it is S to 0. Okay, so the class is 0. Okay, so that's how we do the classification. Consider the open loop transfer function. Okay, meaning you need to get the open loop transfer function of a system, right? And then you check for the highest order at the denominator, order of numerator, and also highest factorial order at the denominator, right? So we do that. All right. So as I mentioned just now, before we start with classification, we classify the system because by knowing the class of the system, the order of the system, we will be able to predict the behavior of the system. Okay, the most common classification that be used to classify a system is order, based on order. Okay, so that's why you maybe have heard me saying first order system, second order system, higher order system, fourth order, 20th order system. Okay, we classify based on the order. That is the common way, right? So by knowing the order of the system, we'll be able to predict that. Okay, we'll be able to predict the behavior. Okay, so now we're going to focus on the first order and second order system. Okay, if it is in instrument, you go also learn about zero order. Zero order straight away lah. It's like static. Okay, but first order, and basically this term is define the behavior at the transient region. Okay, yesterday I mentioned about transient and steady state region. Okay, So first order is actually explaining the behavior at the transient region. Okay. Whether it is first order, second order, third order, it will explain the behavior at the transient region. Right. So let's focus on the first order system. Okay, so the general transfer function for the first order system is k over 1 plus ts. Okay, remember this is closed loop transfer function. Okay, this is closed loop transfer function. Okay, so the general transfer function is k over 1 plus ts. Okay, so if I say general transfer function, you have to make sure that you are comparing to the same form of k over 1 plus ts. Okay, the term is 1 here. Okay, meaning 1 must always be there. Okay, because no, for example, you have 20 over s plus 10. Okay, this is first order. Okay, first order system. Okay, but in order to determine the value of k and t, okay, we need to rewrite the transfer function to be similar to the general transfer function. Okay, so meaning we need to make sure that 1 is visible there. So we need to divide by 10, divide by 10, divide by 10. Okay, divide by 10 because we want to have 1 there. So therefore the general transfer function will become 2 over 10 divided by 10 is 1 plus 0.1 s. Okay, so now you can compare 2 to k and 0.1 to t. Okay, so therefore you will have, if you compare like that, you can say k is equal to 2 and t is equal to 0.1. Okay, so that's why we need to make sure that the transfer function is written in general transfer function, which term 1 here, 1 plus ts, 1. Okay, all right, so what is k, what is t? Okay, later we explain that. Okay, let's go through here. Okay, example of first order. Okay, spring damper system. Remember, we already derived for spring damper system yesterday. Okay, and then thermal system. This is a thermal system. Yes, spring damper because there is no mass, so there is d squared. So the highest order is 1 only. First differentiation, so that is first order. Similar to the thermal system, it just consists of first differentiation, so it is a first order system. All right. Okay, so for this part here, we already derived it yesterday. Okay, if we refer to semalam punya, mana yang semalam? This one. Yang inilah yang semalam. Okay, I believe this one here. Alright, so this is the step to derive the first order system, because this is a spring damper system. We know it is a first order. Alright, so you can refer that to this derivation, and you can see that the highest order is only first differentiation. Alright, and then you apply the unit step input. Okay, and the final equation is 1 minus exponent negative t. Okay, so we're not going to repeat it again here. Okay, so basically this is the same as yesterday derivation. All right, so the equation that we get is yt, bukan yt kan, x not t. x naught t is equal to 1 minus exponent negative t. Okay, because we consider k is equal to 1. Okay. Right, so just refer to the yesterday note. Alright. Alright. Okay. So this 1 exponent negative t is actually derived from the k over 1 plus ts. Okay. Okay. Let's consider the output is y. Ys is equal to, the transfer function is k over 1 plus ts multiplied with the input us. Okay, so the input is ut is the unit step input. Okay, so therefore you have k over 1 plus ts multiplied with 1 over s. Okay, so it is similar to the spring damper system, and then the k is also considered 1. So you have 1 over 1 plus ts multiplied with 1 over s. Okay, so if we derive that, we will get yt we equal 1 over s is 1. Okay, you will do the partial fraction all the step there, but believe me, it will give you the same, which is minus exponent negative 1 over t 1 over t besar 1 over t multiplied with t. Fine. Okay, because if you do the partial fraction, you will have a over s plus b over 1 plus ts. So you get a equal to 1 and b equal to minus 1 over t. Okay. So basically you get this 1 exponent negative 1 over t t. Okay. So this is the general time response equation for first order. Okay. And then yesterday we also have plot the response. Okay, we have plot this one here. Okay. Okay, so we have plot this one. Here is 1 over t. Okay, so if you replace 1 over t there, you will get the 1 over t, tapi this is actually 1 over t is equal to 1. Therefore, t is equal to 1. Okay. Alright, so t equal to 1. Okay. Okay, so the transfer function just now, the general transfer function is k over 1 plus ts. Okay. So k here is the static gain. Okay, or static transfer function. It will explain the behavior of the system at the static region. Okay, the final value will depend on the value of k. Okay, as for the t here, t is the time constant. Okay, so the time constant is defined as the time taken to reach 63.2% of final value. Okay. So T here will explain how fast the output will respond after we apply the input. Okay. T time constant how fast the output responds to the input. Okay, after we apply the input, so how fast the system will respond to the output and reaching the final value. So time constant, we explain this. All right. So here we can see for the example just now, for the spring damper system, the time constant is 1. Okay, why? Because it reached 0.632 at 1 second. Okay, so the definition for time constant is time taken to reach 63.2. Okay, so the final value is 1. Okay, 63.2% from 1 is 0.632. Okay, so from the plot here, we see that for this system, it reached 63.2 at 1 second. So therefore, the time constant is 1 second. Right. So how can time constant be used to explain the behavior, explain how fast the response? Okay. So let's compare 3 types of time constant. Okay. The final value is 1. Okay. So this is Y. This is T. Okay, let's say the first system A is having T equal to 1 second, okay, B equal to second, C equal to 0.5 second, okay. So we know that the output at the time constant will equal to 0.632, okay. So let's consider here is 0.632. Okay. Let's consider that is 0.632. Okay, so meaning let's consider this is 1, this is 2, this is 0.5. Okay, meaning this is system A, this is system B, this is system C. Okay. System A will reach here, 1 second, reach 0.632. System B here, it will take 2 seconds to reach 0.632. And system C will take only 0.5 to reach 0.632. Okay. So if we plot the behavior, okay, because it is first order, we can expect the behavior to be like this. Okay. Right, if we reach 1, final value will be 1. Right. But we can see that, okay, if you compare system A, B, and C, so this is B, this is A, this is C. Okay. So we can see that for system C, it will respond faster, okay, compared to the system A and B. And A is faster than B. B is the slowest one. Okay, this is only by comparing the time constant. Okay, because we are referring to the same point, 0.632 of the final value. We're referring to that. Okay, so we just compare the time. How fast the time will take in order to reach that point. Okay, so by comparing this time constant, okay, we can know system C is the fastest response system as compared to A and B. Okay, that's how we use time constant to explain how fast the output responds to the input. Okay, by knowing the time constant, we will know this system is fast response, this is It's a slower response system. Okay? Any question on the time constant? No. All right. So last one is K. K is static gain. Static gain, or sometimes we know is a static transfer function. Right? So the effect of K here is only at the final value, meaning when the system is already reached the steady state. Okay? So the relationship between Y and U is given by Y is equal to KU. Okay, that's why we consider K is a gain. K is just a value. K is 2, K is 3, K is 10, K is 0.5. Okay? Okay. All right. So we already know the final value here. Okay, is 1. Okay. The input is unit step input. Right? Which is also 1. Unit step input, unit 1. Okay, so we apply unit step input. We can expect the output is 1, but it's also depend on the K. Okay, if the output is 1, then we get K is equal to Y over U, which is 1 over 1. K is 1. Okay, but if K is not 1, K equal to 3. Okay, so U is K, Y is equal to KU. K is 3, multiply with U is the step input 1. So we can say that the final value we reach 3. Okay, so if the final value we reach 3, so 63.2% multiplied by 3. Berapa tah? 1.8 something maybe. Okay, so that is the time constant will not be 0.632 anymore. It will be 63.2% of final value, which is 3. Okay, so we can see the effect of K by plotting the graph. Okay, T. Right, again let's consider 3 system, A, B and C. With the K, the 1 is 1, B is 2, C is 0.2, 0.5. Okay. So by calculating the U, Y, okay, consider the input is unit step input. 1 multiplied with 1 is 1. 1 multiplied with 2 is 2, and then 1 multiplied with 0.5 is 0.5. Okay. So therefore, let's also consider the time constant is the same. Time constant is 1. Okay. So I'm going to plot. Okay. So alright, so we know the time constant is time taken to reach 63.2%. Okay, so therefore for A it is 0.632. For B is 1.2 something. 1.2 berapa? Try to multiply 0.6. 63.2% from 2. Okay, and then 0.5. Berapa? 63.2 from 0.5. Anyone?
0.316.
0.316. Yang ni 0.26 eh. Okay. Okay. So we can expect the first one is let's say this is 1, this is 2, 1, 2. So 0, this is 0.5. So let's consider here 0.3. Okay. Then the second one is 0.6 around here. And the one is this one here. Okay. So if you plot that, so this one will be reaching 0.5. Okay. This one will be reaching 1. And this one will be reaching 2. Okay. So K will affect the final value of the output. Okay, if K is 1, then you apply unit step input, the output will be 1. But if the gain is 2, 3 or lower, then you can see the final value will depend on the value of K there. Okay, Y multiply with KU. Okay, so that is the effect of K. It will amplify the transfer function. Okay, so if we write the transfer function for the first system, A is K equal to 1, so 1 over 1 plus S or S plus 1. Okay, that is the transfer function for the system. Or Y equal to Y over U equal to 1 over S plus 1. Mana tu? Okay. For B, let's say B is 2, right? So it is 2 over S plus 1. Okay. C is 0.5 S plus 1. Okay. The 1, 2, 3 is the K, and then here we have T here. TS, right? TS. So here T equal to 1. Right? So this is for the graph here. If you refer to this graph here, we can write the transfer function. The transfer function for A is 1 over, because the final value is 1 over S plus 1. Okay, T is 1. B, 1 over 1 plus 2S. Okay, and C is 1 over 1 plus 0.5S. Okay, that is the transfer function that explains the behavior of A, B, and C for the time constant effect. Okay, and this one is the transfer function to explain for the gain effect. Okay. Any question on that? Okay, let's do the example here. Okay, there is only one example for first order. Maybe I will share the past equation. All right, so example 1. Okay, the transfer function which relate the input voltage V, okay, to the output torque. Okay, so the transfer function will be torque over voltage, okay, will equal to the first order transfer function. So when it says first order transfer function, we write the general transfer function K over 1 plus TS. Okay, all right, and then it said a time response test with a 6-volt input voltage resulting in a steady state output torque of 20 Newton centimeter. Okay, so meaning here V is equal to 6. Okay, because it apply the input 6 volt. Okay, meaning it's changed from 0 volt to 6 volt. Okay, and then if we get Y steady state ataupun bukan Y lah, torque steady state. Okay, because it said that steady state output torque is equal to 20 Newton per Newton centimeter. Okay, so we know this is U, this is Y. Okay, so from there we can determine the K, because the equation is K is equal to Y over U. Okay, why? Because the information given here is at steady state. Okay, so for steady state, it will relate to K. Okay, so therefore we can calculate K. So it is equal to 20 Newton centimeter divided by 6 volt. So K you will get 3.33 Newton centimeter per volt. Okay, that will be the K. Okay, because it is the value is in steady state, so it will relate to the K. Okay, the last information is it took 0.4 seconds to reach 12.6 Newton per meter. Okay, so let's find the transfer function. So meaning you need to find the K, you need to find the T. Okay, so we already know the K. So K is 3.33 divided by 1 plus S. So we need to find T. Okay, so it said that 12.6. So if we plot system T, okay, we know the final value will be 20. Okay, 20 Newton cm. And then it mentioned that with 12.6. Okay. Okay. So if you calculate 12.6 here, okay, 12.6 is actually equal to 63.2% multiplied with 20. Okay, 63.2% multiplied with 20, it gives you 12.6. Therefore, it said that it reached 12.6 at 0.4 seconds. So this is T, time constant. Okay, because T is time taken to reach 63.2%. So 63.2% is 12.6. So therefore, 0.4 is our time constant. So the answer will be 0.4 S. Okay, so that will be the transfer function for the system. Okay, 3.33 over 1 plus 0.4 S. Okay, so basically that is how we can predict the behavior of the first order system. Okay, basically the response will always look like this. Okay, we already proved that. It will respond to the shape will be based on the exponential shape there, 1 minus exponential. Okay, and then okay, we can determine the final value based on K, or if you look at the graph, we can determine the K by looking at the final value and then multiply with the or divide with the input signal. Okay, and then we can determine the time constant by looking at the 63.2% of the final value. What is the time taken to reach that value? Okay. So I already explained that a time constant will explain how fast the system responds, and K will explain the steady state behavior. Okay, at the steady state, what is the final value at the steady state region? Okay, from there we can determine the error and etc. Okay, but that one is for later part. Okay, as for the first part, the equation will always be kalau in general form for the, saya tak bagi. For the YT, the general form will be K multiplied with 1 minus exponent negative